Good morning, everyone. Welcome to CalPlug's 10th Anniversary Celebration Workshop. It is my great pleasure to be here. My name is GP Lee. GP stands for good person. I won't become a great person until we all solve climate change challenging problems. Please help me, help everyone, help the entire community to solve their problems. And so this is the 10th anniversary celebrations. So in our last 10 years, the focus of CalPlug has been on plug loads, mainly on electronics, consumer electronics, and so on. And starting about a year ago, we worked with our advisory board to come up with the new vision for the second decade of CalPlug. So the consensus with the new vision is we will work on energy conscientious plug and process load for everywhere people work, live, and play. So basically, there are two major loads we have to deal with in order to deal with the climate change issues, plug load and process load. So with those two major focus areas, what we will do is to bring in energy efficiency and the flexibility to the plug and the process load. That is what we will do in the second decade. With all of your help and support and contribution, we can work together to help me to become a great person. Thank you. So at this time, I want to take this opportunity to thank all the audience. I know this is our first time to have an in-person meeting, and after the lockdown. I'm so happy to see so many friends and new friends and the new champions for this new era of the process and plug load research. Also, I want to thank today's speakers for their major contribution to really bring some of the most recent advancement in their solutions in terms of climate resilience solutions. And lastly, I want to thank all the CalPlug staff members to put this program together. I know I won't stand here without their support. I can only do this. They do real work, okay? So, in order to support this climate resilience solutions, and probably you notice we do not have the paper for the agenda. I'm setting the back example because I need to read out the speaker's bio. So there is a QR code. You can see it, the meeting's agenda, like what we have today. In the morning, we have the speaker, and then there's a lunch, and afternoon, again, a presentation, then we have a reception, and the roundtable discussion and the receptions at the end. So enjoy this network session. I think this is, to my experience, most exciting to me is to have a chance to interact with so many people, to learn about what they do and come up with new ideas and for collaborations. And also, I'd like to take this opportunity to thank all the champions in the last 10 years and for their contribution, and from the advisory board member to chief technology council members for their guidance and leadership to help us to grow. And lastly, I want to thank, this is a special thanks to all the sponsors. Without their sponsorship, we won't be here to promote this agenda. And by the way, when you go out to the atriums, on the screen, you can see the slideshow for all the activity has happened in CalPlug in the last 10 years, including the Department of Energy Secretary visit, and also, I think it's the executive director, I don't remember the name now, It was in 2016, and the CEC's commissioners visit, and many good memory of the member here in the last 10 years. So enjoy the slideshow outside in the atrium. So without further ado, I'd like to start today's program by inviting two co-chair for the advisory board to give opening remarks. So the first one is Dr. Kim Trenbath, and she is an innovation lead in NREL. NREL is one of the very prestigious DOE labs. So Kim, please.
All right. Hello, everyone. Again, welcome to CalPlug's 10th anniversary celebration. I want to thank the speakers. I also want to thank all of you for being here, and thank you to the CalPlug team for hosting this event. I'm Dr. Kim Trenbath. I'm the lead for the Systems Technology Research and Development portfolio in the Building Technologies and Science Center at the National Renewable Energy Laboratory, and we are located in Golden, Colorado. We are a U.S. Department of Energy federally funded research and development center. Along with Doug Johnson, I'm the co-chair for the CalPlug Advisory Board. So welcome again. So today's workshop title is Designing Climate Resiliency, Energy Load Solutions at the Intersection of Infrastructures, Community, and People. And I love this title. I think it's very appropriate for where we are right now and very appropriate for CalPlug. And I'll tell you two reasons why. The first reason is that this topic is very holistic. So what do I mean by holistic? There's technical components to it, but there's also a people component. There's a behavioral component, policy, possibly standards and codes, economics, social, and other aspects to it. And this is in line with what we are trying to do when we're trying to solve climate change. We need these holistic solutions. The other reason why I'm excited about it is that it definitely relates to CalPlug's work over the last 10 years. This type of work that they've conducted is work that is needed for us to successfully decarbonize. CalPlug contributed to the technical research and critical behavioral research on people's interactions with infrastructure and the resulting energy impact. So hence, CalPlug's work to this day has been very holistic. So now we're making a shift, and this is a national shift. Perhaps California is already there, but nationally we weren't until recently. We're shifting from focusing on solely energy efficiency to these more strategies that are a little bit more holistic, and we're focusing on zero carbon, things that can decarbonize our built infrastructure. So the US Department of Energy has a goal for achieving zero carbon by 2050, and it's starting with decarbonized power sector by 2035. And in order to meet this goal, decarbonization needs to be possible in all communities. So what does this focus mean? Well, I'd like to break things down by opportunities and challenges, so that's what I'll do. So there's lots of opportunities, and I'll go over a couple of them, but there's a huge opportunity here. First of all, there is a market opportunity that is happening right now. This is incredible. There are new markets that are available for us to tap into. There's also new markets for the graduates of institutions like UCI to go and work at. And a good example is electric vehicles. When I graduated from college, there wasn't really a job for me in electric vehicles, but now there is, and you can be majoring in anything. You could be majoring in engineering, you could be majoring in communications, and you could have a job in that market, which I think is great. The other opportunity is the equitable energy transition. So we're trying to transition into cleaner technologies, reducing our, mitigating climate change. There's an opportunity here for us to work in this area, as well as recent graduates to work in this area. And those recent graduates know that this is a challenge that they're going to be addressing for the rest of their careers. So here's an opportunity for us to help the workforce along and continue the legacy that we, including CalPlug, has built over the past 10 years. So there's also challenges, and some of these challenges are related to some of the opportunities. So I said new markets. So some of these new markets are not necessarily clean and green. Can anyone think of a couple new markets that are opening up? I'll answer my own question. So there's a great opportunity. There's a new market with cryptocurrency mining, right? And we all know that that is using a lot of energy. And I do see this as a challenge because there's not a really good solution to reduce the carbon impact there. So we got to be working on that. Other challenges that we talked about during the advisory board meeting yesterday was things like retrofits. So retrofitting the old infrastructure to be climate resilient and zero carbon. And another challenge is this holistic approach. It's important to have a holistic approach, and CalPlug has been one of the leaders in this holistic approach over the past 10 years. But we need to take that holistic approach that CalPlug has developed and scale it up, not only for plug loads, but for all technologies. And things like working with small to medium enterprises, workforce development, teaching students, understanding the behavioral aspects of how people interact with plug loads. These are all things that we need to understand in order to reach our climate resiliency goals. And again, CalPlug is the leader in this area. They're a leader in the research, the holistic approach, and what they've done over the past couple years that GP alluded to is they've converted their expertise to this approach for climate resilience. So I want to take one last moment to talk about how CalPlug has focused on plug loads, one of the building end uses, over the past 10 years. So I work in plug loads, and plug loads account for 47% of whole building energy use. Plug and process loads, account for 47% of whole building energy use for commercial buildings. And that's significant. And it's significant because it's a chunk of the pie that's hard to address, and it also has technical components as well as behavioral components. These are, as you know, the plug-in devices that not only do we need to address with a technical solution, but we need to address with understanding the behavior and then potentially management solutions. The possibilities are endless. Now, historically, we've focused on some of the easier end uses to target, but I think there's a big opportunity now that we're focusing on zero carbon moving forward to really tackle plug and process loads. Because if you want to get to zero carbon, you have to come in with a good solution here. And one of the solutions could be, 100% renewable energy for this load, but I don't think that's the most efficient way. I think that's going to be quite expensive. And at the same time, we need to consider all the people, all the communities that are going to be impacted. So I'm excited to see CalPlug expand their work with PPLs to greater resilience efforts. And I'm excited to see them work over the next 10 years and beyond, making an impact, scaling it up from before. And I want to congratulate CalPlug for 10 years of excellent work, truly being a leader in plug and process loads research. So thank you very much. And at this point, I want to turn it over to my co-chair, Doug Johnson.
So while we're getting the slides, are they switching back there? Okay. Well, thank you, Kim, for those remarks, and I'll join you with my hearty congratulations to CalPlug as well, and gratitude really for being able to to serve with Kim on the advisory board, to participate in any number of workshops and projects related to CalPlug over the years. And it's likewise reflective also of our industry's involvement and gratitude as well. And as we're, oh, there it is, yep, terrific, thank you. And since we're, at the 10-year mark, it's, I think, worth talking about anniversaries. And when I was thinking about anniversaries, well, it comes to mind wedding anniversaries, and I was kind of curious what happens at 10 years. I couldn't remember. So Hallmark has a website, and they list all sorts of themes all the way to year 60 here. But I find that at 10 years, they talk about tin and aluminum. So I might have a can for you or something like that, GP, but not very exciting, although who knows, because we'll hear it maybe from our subsequent speakers, but elements and minerals are playing a pretty big role in electricity storage and power. So I was curious what else appears on the list, and well, I think we're going to have to wait another 8 years to talk about appliances. All right, so that's a little early for that. And more so, I'll see you in another 34 years to talk about my industry, electronics. Okay, so that's in the future gathering of CalPlug. So electronics has been my focus, my angle on energy efficiency and working with our member companies and the broader industry, which includes startups, as Kim mentioned earlier, but also major multinational companies. We all in my industry and many others play an important role in environmental sustainability, and in the area of energy efficiency, play a role in how products are designed to be more energy efficient, how they can be used to manage energy use, and of course how they're dealt with at the end of life, which also has an energy component to it as well. But in looking back at CalPlug's past 10 years, I thought, well, what are the themes or concepts that stand out prominent in my mind? And one of them is certainly data. I've looked at CalPlug as an opportunity for interested parties to come together and talk about what data do we have, what are we seeing, what can we analyze, or what do we need to go out and collect. And CalPlug's been a great resource. Students, I think, graduate, undergraduate, making contributions. I think some of our member companies over the years have engaged in very specific projects and collaborations to look at power consumption in equipment such as set-top boxes, collect data, experiment, see what can be done to maybe save a few watts here and there. And it all adds up, as we know, to big numbers. So I think of those students and researchers. I also think about partnerships with industry when it comes to data collection. And I think also frequently, and always have the past 15 years as I've worked on energy efficiency, about how we can make our own contribution of data as an industry player, as an industry organization. And just last year, as GP knows, because we share the results with them and certainly talk about it, we've undertaken a census of energy use in our own industry. Okay, so all the plug loads and electronics in the home. We take a look at that nationally and sum it all up and share that data with researchers and policymakers and kind of benchmark ourselves over time. So we've done that every 3 years for 15 years. So our 5th study just came out last year. And all that's very important to keeping track of progress and informing people about policies and programs. Policy actually is another concept that comes to mind. And I know the byproducts of CalPlug's work have informed policymaking. And policymaking, when it comes to energy efficiency, encompasses at least 3 general areas, each of which has quite a long history. In some cases, there's traditional regulation, appliance efficiency standards. Gosh, I think they're about 4 decades old now. So CalPlug's 10 years old, and we've got maybe a 40-year history in California and at the national level in government-led energy efficiency standards. We have about 30 years of Energy Star already, right? 3 decades of the voluntary, market-oriented, consumer-focused Energy Star program, which has done a great job in a lot of sectors and a lot of product categories. Our industry's been deeply involved in that. And CalPlug's research obviously supports both the voluntary and the mandatory. And very recently, relatively speaking, we've had voluntary agreements. That is industry getting together with non-industry stakeholders in some cases to come up with an additional voluntary way to move the market, to transform the market to higher levels of energy efficiency. We've done this for set-top boxes, and CalPlug did some early research related to our first generation set-top box voluntary agreement. We've done it for small network equipment, modems and routers, and we're actually working on it now for televisions. And also when it comes to policy and the theme of resilience that Kim referenced at the beginning, in addition to GP, I think of the resilience of some of these programs, like I said, that have been around a long time and seen the ups and downs of the economy and the pandemic most recently. So these policies and programs are in for the long run. They mean a lot to the industry. Some are better suited to some sectors than others, but they're all out there, and they're all informed by the research and initiatives that we see here on campus. Lastly, collaboration. Very important to collaborate, industry and government, academia, NGOs. The best comes out of that sort of thing, and we've seen it in those policies and programs that I've mentioned. It's important in general in policy making, particularly when it comes to tech industry products and equipment. And we are better informed with policy making as a result of that collaboration. I mentioned that we're focused on televisions right now with a voluntary agreement. And our work already to date with televisions has been great in terms of collaboration, and this is something I look forward to talking to CalPlug about too. But we've been able to come together with energy efficiency advocacy groups and improve the way we measure power consumption. And so the experiments and lab work that goes on at CalPlug depends on standard test procedures or consideration of new standard test procedures. And all that helps us measure in a standard way and create these programs around that category. So it starts with a current, up-to-date test method. That's what we're doing in televisions. And lastly, I think it's crucial that we have that collaboration. It's been a theme in the past 10 years. It's going to be important as we tackle new problems and challenges, not only in my industry, but across all plug load sectors. And I look forward to being a part of that. Obviously, our members do as well. So with all that in mind, I look back and I look forward to the past. I look back in the past 10 years, and I certainly look forward to the next 10 years with all those concepts and accomplishments in mind. Thanks very much. At this point, back to you, GP. I think you introduce our next speaker.
Okay, thank you. Okay, so it is my great pleasure to introduce today's keynote. As Kim just mentioned earlier about the greatest excitement in the market is about EV, but without the battery, EV will not run. So today is a great pleasure to have Benjamin Park, who is co-founder and CTO of the companies. You can introduce your own company to talk about silicon-based battery. This is really new. When I think about silicon, it's so cheap. So in my mind, can this be really truly affordable and 10 cents for everybody? Please, Benjamin. This is US. This one.
I have it on a USB stick too if you need.
Okay.
Is there a USB plug?
No, because something is wrong.
I
with
tested,
it.
it should work.
It should work. Do you know why?
Which one was it? This one is
Yes,
it?
yes.
I think it's a software problem, not hardware.
Do you have another copy of it?
USB stick. Yeah, USB.
Yeah.
Thank you.
Do you want the full screen?
Yes, please.
Alrighty, thank you very much. I think Kim and Doug had a great introduction. I'm not as good a speaker, but I'll do my best, I promise. Thank you to the organizers, thank you to Patricia, thank you to GP Lee. This place brings back a lot of memories. I started the company when I was actually in this building, and the amazing thing is you haven't changed, while I've seen a lot of degradation over the years. So I'm gonna have to figure out what the secret is, because I definitely don't have the secret. So today I'm going to be talking about solving difficult problems together to help mitigate climate change. So usually my talks are very focused on like technology, like what happens in the active material. But I decided to change maybe my normal talk flow to address some of the stuff we've been seeing out there tied to what we're doing with our electric vehicle partners, as well as what's happening on the charging side. So that's going to be the focus of my talk. Let me talk a little bit about Enevate. So Enevate is a company I founded a little bit over 17 years ago now. Who knew? But it's been a fun ride. Our mission is to develop innovative battery technologies to accelerate adoption of electrified mobility. That's our mission, but our vision is to have a cleaner, sustainable environment through a variety of battery-powered applications. So actually, the whole company vision is focused on cleaner environment, on climate. And I think we take this very seriously. A lot of companies do this just because it's maybe something that's good for marketing. But I can guarantee you, probably more than half of my team would leave immediately if we said that our focus was on just profits or something else. So it's an interesting thing, and it really, really feels good to be part of such an effort, part of such a community. And I'm not talking about just us as a company. I founded the company in 2005. I have to mention we have a lot of UC Irvine Anteater founders. So I don't know how many of you here are affiliated with the university, but if you are, say zot, zot, zot. This is the response I get everywhere. So we need to be more enthusiastic, but good try, good try. So our business model is somewhat unique. Our business model is not to let's make the stuff, let's ship it. I think a lot of people have tried that business model. What our thinking is, why don't we just develop technologies? And there are a lot of big, large companies who have the infrastructure, who can make the large investments to build gigafactories, terafactories of batteries. Even automotive companies are talking about and planning to build their own batteries. So why do we need to be in that space? We don't. We can develop technologies with a good environment and then supply those technologies to the companies out there. So we can think of ourselves kind of like the ARM or the Qualcomm or a semiconductor, the NVIDIA of the battery space. So we develop technologies and we supply that to our companies. So we've had our technology tested by well over 20 different companies out there, probably most of the tier 1 auto and battery companies. So we're very proud of that. We're very proud of our partnerships because we know that we're not just in this ourselves. We have to be working with everybody else. And I think that's impressive to me because that's the theme I heard with all of the introduction about CalPlug. So I think we resonate well with that because we know that we're part of an ecosystem. And if something breaks in the ecosystem, it doesn't really work. It has to be everybody working on this together. So let me talk a little bit about our partners. So we have a lot of investors, partners, and customers who are really working hard with us to make this a reality. So we have Renault, Nissan, Mitsubishi. It's called an automotive alliance. We have LG Chem, Samsung, Fidelity, and Enertech. So, again, it takes a ecosystem to make things work. Of course, we're working with a lot of companies that we can't name yet due to certain agreements, but we've been very happy with the support we've had from the industry. So let me talk a little bit about our technology and what the technology does. So we develop a technology, and it's not just an anode thing. A lot of people confuse us as an anode company, but it is really difficult to engineer a battery if you change one component. It's kind of like Domino's law. If you change one thing, you need to change this. You end up designing the entire cell. So we're a cell technology company that's focused on material changes that customers will really like. So what would a customer want from a vehicle ownership point of view? And 10 times faster charging was one thing. A lot of our customers, and we quickly realized that we really need to have this faster charge. And I'm going to talk more about that later, but very rarely in the chemistry space is there something where you can have like Moore's law, like a 10x improvement. In the battery space, we usually celebrate 5%, yay, but a lot of investors are not that happy with that. But this charge, that is something that we can really, really improve by a huge margin, by order of magnitude. But usually, if you do that, you miss out on some other things. So for example, you can make a fast charge battery today. What would it look like? So if you made a 15-minute charging battery today, with today's technology, you would make very, very thin layers of material. You would have thicker foils. So what happens in the end is the battery loses the energy density, and then it loses the cost advantage. So it becomes 2 times more expensive, roughly 2 times more expensive, and roughly half the energy density. So this is studies done by the Department of Energy. We're seeing it in our designs as well, if you use conventional technology. Our advantage is that we can do that. We can get the faster charging, but not lose out on cost or on the range, which are important for consumers. So we can have a 30% longer range. We have better low temperature performance, which is important. We have a safer battery. I could talk more about that later. Higher efficiencies, and we actually can also have a lower cost, and that's very important for the consumer. One of the key things that we've done that other companies have not focused on as much is as we're going through this process, we're testing these large batteries with the automakers and battery manufacturers, and we're now at the stage where we have to prove out the CO2 advantage, right? So I don't know how many of you are familiar with that, but companies can't actually make statements, at least in the United States, tied to CO2 emissions without having a third party back up the research. So we've worked with third parties and our customers to show that we can deliver up to 26% CO2 gas reduction in the manufacturing of an electric vehicle. So as many of you may or may not know, the electric vehicle will save a lot of CO2 emissions versus an ICE vehicle, internal combustion engine vehicle, during its normal usage. However, during manufacturing, that is where there is a lot of CO2 emissions. So we are targeting the manufacturing manufacturing piece of it, and batteries make up a large part of an electric vehicle. So we're very happy to be able to report that. So I'm not going to go into every one point here in detail because I've already mentioned some of it on the previous slide. But basically, there are pain points for EV adoption. Some people are saying, oh, maybe the carbon footprint is not as good. Maybe the charge time, it makes it impossible for adoption. They're too expensive. People can't buy it. The driving distance is too low. I drive this much. I can't buy an EV. You may have heard all of these different pain points out there. So we made a list of these. We ranked them. We looked at surveys and everything. And we went to start developing a technology that would address these pain points one by one. So that's what our technology matches well with. So we address carbon footprint. We address charging time. We address price. We address driving distance, low performance, safety, and efficiency. So this is kind of what we do. And now we're looking at other markets as well. But of course, we're laser focused on launching all our products in this space first. So what makes us so special? What have we done over the last 17 or so years? Well, what we've done is we've developed a system to really test things fast. So for example, if you get a group of scientists together, you'll have a ton of ideas, right? So all companies have really bright scientists, but the real question is, how quickly can you convert an idea to a result? And we focused on that. We focused on systems. So what we've done is we've, on average, reduced that time to about a third versus what other companies or other labs do. So how do we do that? First of all, that's one of the reasons why we targeted fast charge, because if you can fast charge, fast discharge a cell, you can get the durability testing much faster than other battery test houses. So we've done that. We've also made a system internally. So we haven't purchased a system or anything. We've developed an in-house system where the data is collected into a cloud, and all of that data is pre-processed to the scientist. So if a scientist wants a graph a certain way, you'll have that delivered in real time instead of having to ask for somebody, getting the file, importing the data, and then graphing it. We have all of these templates pre-processed in the cloud so that somebody could pull it. So what has that resulted in? It resulted in 4 generations of technology, about 1 million meters of electrodes produced. Our core technology is the anode, even though we have technology around the cell. And we're not a production house, but our partners needed that much material to kind of jumpstart their manufacturing efforts. And we have 3,000 channels, which means that we can test 3,000 batteries at a time. In total, we have about 1,500 years worth of cumulative cell test data, and that's about 4 billion data points. So one of the most exciting things that we're doing in my team right now is actually working on that data using machine learning, and now we're getting very, very interesting counterintuitive results that now are helping adoption of new technologies, not just silicon, but a lot of the low nickel technologies. For example, lithium iron phosphate has a very, very flat curve. It makes it challenging to fuel gauge because usually if you know roughly the voltage, you can know how discharged your battery is. But if it's very, very flat, it's just like, oh, and then it suddenly dies off, right? So you need other signals, and we're finding that we have the capabilities to address that. So we're very excited about that field. So how do we achieve this? Well, we achieve this performance through mainly 3 pillars. I call them the 3 pillars of our technology. The first is a silicon-dominant anode. So what does that mean? People have been talking about silicon for a long time. Silicon can store roughly 10 times as much lithium as graphite. Graphite is the conventional anode. Silicon is very abundant everywhere, right? Basically, all sand, dirt has silicon in it. But what we've done is different. What most people have worked on is a completely mildly evolutionary approach or a completely revolutionary approach. So people are talking about, for example, mixing a little bit of silicon with graphite. That's what you see in commercial cells today. So when they say silicon anode, most of it is graphite with just like a few % of elemental silicon. So that's what I call mildly evolutionary. And then the revolutionary is people are saying, okay, we're just going to use lithium metal and then solid state. And we're interested in solid state too, but remember lithium metal cells were commercialized first before lithium ion, and then there were issues with them. And I think a lot of the fundamental issues still haven't been solved. They're making a lot of progress on that. But we're kind of not this or this. What we've done is maybe simplify the system a little bit. We were thinking, if you have graphite and silicon and you're trying to use both, it makes it incredibly difficult. So why not simplify the system and just use silicon, right? So we were the first ones to do that, and we're able to get really good results with that simple a system. And we could do that because the silicon we use is very inexpensive and very, very eco-friendly in terms of how it's made. We're not using silane or some other hazardous gas to make it. We also have electrolytes and additives. So that's the liquid that you have around the silicon, and this kind of acts in harmony with the silicon to make it perform. And then we have cell design and cell formation. So once you have everything in a cell, how you initialize the cell at the factory it actually has a huge impact on the overall lifetime of the battery. And we have a lot of know-how in that. So how do our cells perform? Well, on the right, you'll see some charge graphs. These are from our cells. But conventional graphite cell, roughly 1C in terms of charge rate. What does 1C mean? It means let's say give or take an hour to charge. I know you'll say, oh, I can charge this in this much time. This is just the rough, take for a graphite cell. If you do charge a graphite cell with a higher speed than this, you typically start hurting its reliability. And you'll see that even in studies out there on how often you supercharge, for example. In our cells, we're able to charge between 4C and 10C. Most of our customers are targeting a range in between that. So what does that mean roughly? That means roughly a charge time of, let's say, 5 minutes to 75%, or roughly 15 minutes to let's say 80% charge. So that's roughly the time frame which our customers are focused on, mainly because that's enough to replace a gasoline vehicle fueling experience with an electrical charging experience. So what do I mean by that? Well, today, even for the faster charging electric vehicles, you still have to change your behavior. You can't go to a charging station like you would a gas station. You can't just wait there. It's still too long for that. And again, that is an important part of customer adoption. So I'm going to be very short on this slide. Basically, silicon is more energy dense. So the anode becomes thinner, yet stores the same energy. That's the fundamental basis around the technology. But again, it's a cell technology. So it's everything around that makes it happen. On the right, the SEM is very interesting. It's a colored SEM. That's an SEM just showing our anode. It's much thinner than conventional anodes. We're talking about 30 microns. So it's a very, very thin anode, and we've made a lot of it over our lifetime. So I want to address a question I still get asked. Why bother with fast charge? Who cares about fast charge? It's something I care about, but let me explain why. Only about 1 out of 5 cars have access to overnight charging. What I mean by that is the owners or that car, the location for that car. Like if you look at all of the vehicles out there in the United States, only about 1 out of each of the 5 ones would have a place where you could park overnight and have access to electricity where you can install a charger. So what do you do with the rest of the 80% of the owners? Fast charge is an approach. Some people have asked me, what about battery swapping, right? Battery swapping can solve it without fast charge. But the battery swapping companies are coming to us. Guess what? If you do battery swapping, you have to eventually charge those batteries. So unless you want to hold an extremely high inventory of batteries at each charging station or battery swapping station, you still need fast charge. Otherwise, you just have to carry a huge amount of batteries. Also, it improves existing infrastructure. So, some people have asked me, well, all right, these ultra-fast chargers, they're years away. Why do we need fast charge now? I mean, you could look at the data, but for example, whether you take a Tesla, a Bolt, or any electric vehicle, you'll know that it charges at its fastest rate for some time, and then it immediately drops off. Why is that? The battery maximum charge rate is dependent on state of charge. So as you charge the battery, the speed at which you could charge it goes down. So the charging regime is always limited by the battery chemistry. So that's kind of what we want to address. If your chemistry can handle that and it's no longer the limit, basically that means with existing chargers today, without having to build out anything, your charge time will be much faster. So it depends on the car and the charger. We're talking about up to 2 times faster without changing any of the infrastructure. That's huge because somebody has to pay for the infrastructure and somebody has a return on investment for the infrastructure. So utilizing it more efficiently is very important. And finally, we need to support drivers in becoming more comfortable with less expensive vehicles with shorter range. Because right now, everybody wants an electric vehicle with a longer range. And I don't blame people because it is a bigger hassle if you have to charge, mainly because charging takes so long. If you can get comfortable, if you can get rid of that range anxiety, then smaller cars become much more reasonable to a consumer, and the smaller cars, guess what? They're easier to fast charge. Because now if their battery packs are smaller, with the same size charger, you could charge it at a faster rate, right? Because everything's relative to the size of the pack. So let's give some examples of that. So here are some examples of, here you'll see some Model S's, but you can find graphs of everything out there. They're all there. They're all very similar. So basically, you'll see, the max charge in the beginning, and then it starts going down. Same thing with the Model 3 on the right. Basically, you can't charge at the max rate, and this is very important because we have the infrastructure, but we're not using it efficiently, and it's mainly driven by the chemistry limitations of the cell. So for example, for chargers in the 40 to 200 kilowatt range, you can charge up to twice as fast. It's not quite twice as fast for most, as you can see from that graph. Just imagine if you were charging at the max rate for most of the charge, that's the difference that you would see. But a lot of the cars don't charge as fast as this, right? So again, you can look up the cars out there. But for 300 plus kilowatt chargers, which are already commercialized, already out there, the efficiency can be improved by roughly 3x. And that's something our partners are very excited about, because that now enables certain business models that weren't possible before, right? So people want to do good things. People want to, help the climate, but oftentimes the business case doesn't support it, right? What we're trying to do is create technologies that enable business cases so that it's easier to do things that help the climate. So let's talk a little bit about charging equipment and infrastructure. Long story short, charging infrastructure is somewhat expensive. So we're talking about $50 billion from a McKinsey report to ensure public charging in just 3 areas. This is US, Europe, and China alone. So globally, it's an even higher number than that. This was a while ago. So with the inflation, I don't know what that number will be, but it's definitely not 50 billion anymore. At that time, they were estimating around 11 billion for the US. So reducing or utilizing whatever investments we've made in the charging infrastructure already and making it more efficient in the future is key. And for that, fast charging is an absolute requirement. Now let's talk a little bit about the grid. Now this, I have to admit, these next few slides are going into a place I'm a little bit less familiar with, but we've had a lot of conversations with various energy companies, charging companies, and electric vehicle companies who are also looking at this space. But I will say I'm knowledgeable enough to be dangerous. So what I'm going to do is some of the references here, if you look at them, they're not the best references, but they reflect my conversations. I didn't want to say, I talked with this person at this point, and this is what that person said. So I captured some of the references, even if they're not the best sources, that reflect some of the conversation I've had so I could point to something public. So let's talk a little bit about the grid. I think recently there have been a lot of press about the grid's not going to be able to handle this. The grid's in trouble, but that's not really what we see, at least with the companies that we're working with in the long term. So the grid is going through the largest transformation in history. A lot of coal and nuclear plants are transitioning to natural gas, to fracking in the past, but also wind and solar. So wind and solar are now being so cost efficient that it's just the uptick is crazy. But there's a lot of stress. So the extreme weather that climate change is I guess, making more, even more extreme, is putting stress on the grid. And for example, in California, the drought is reducing hydroelectric output. And in addition to this, wind and solar fluctuates a lot. So it's been a challenge for grid operators. So they're looking for things like energy storage or things like other ways to handle this, because it's happening at a very rapid pace. In fact, a lot of the plants that they had originally planned to be operational for a certain time are now being decommissioned due to various pressures. So they're trying to figure this out. At least from my vantage point, and with the conversations we've had, this is an issue. It will likely get worse before it gets better, but it's mainly a short-term issue. In the long term, I think everybody still is going after these climate goals and looking towards climate resiliency. So in the long term, let's talk about what that means in terms of calculations and such. So if every American switched to an EV, analysts estimate using about 25% electricity than today. You may be thinking, wow, that's a lot. Or you may be thinking, oh, that's not much. It is what it is, 25%. It may require some new generation and transmission networks, but this is not wildly outside of the range in what we can engineer and what we can handle. Even the most optimistic targets, though, are about 50% by 2030. So it's less than this. So I think we can handle this. Local generation, people are planning on. I'm not sure if it's that popular with the grid operators, but a lot of other companies are working on this. That should help lessen the load. I think in California, it is to the point where maybe the adoption has been too rapid from the perspective of some of the companies we've been talking to. So as long as there have been some hit pieces in the media, like, you won't believe this, I can't believe this, I read it either, but some articles were like, hey, if all of the electric vehicles, if all the cars were transformed into electric vehicles and you charge at the same time, the grid can't handle it. But that's kind of obvious. Like if we were all charging gasoline vehicles, fueling gasoline vehicles at the same exact time, would our infrastructure be able to handle it? No, it's a ridiculous argument. But in any case, some people like making arguments. It sells a lot of articles and ads, right? But as long as all cars are not charging at once, the grids are mainly fine. So I'll give you some examples. So in the UK, for example, the total energy required for all EVs, for total electrification, is roughly 70 terawatt hours. The grid produced 323 terawatt hours. So, that's roughly 20% of the grid, which is, again, not outlandish. In fact, the grid fluctuates in terms of how much it generates depending on demand. So in 2005, it had already produced 402 terawatt hours. So it's not a problem, at least in the long term. Again, short term, there will be pain. So both sides can be right. There can be pain, but eventually people are working on the very difficult problem. In the US, it's similar. The US, the driving distance is long. Car culture is a little bit different, so it's a little bit higher, and in that it's 27.6% versus 20, but it's still manageable. And I know every entity we're talking to is planning around this and working towards this. So how can we handle fast charge? Now that we've established that the grid can handle, the charging itself. So one of the things is to plan ahead and have storage with the EV charging stations, because the storage really mitigates some of the direct impact on the grid. And then pricing incentives to adjust EV charging demand. That's also something that people have been talking about. Again, it may not be as popular with customers in the beginning, but that is basically the most capitalistic way of adjusting demand. And it really works because you look at electricity prices for your home, for EV homeowners, they charge because of the plan. And people I know are planning on this for even charging, although there are some regulatory requirements around that. So it can be planned, it can be mitigated. One of the interesting things that we've been hearing is that fast charging can also help with this transition. This was something new to me. It was in recent discussions I've had. Basically, with smart fast charge stations, what you can do is you can now mitigate some of the load from solar. So it turns out the load demand for fast charging is very different from the demand for normal charging at home. So for example, for charging at home, you're charging overnight, you're not typically charging during the day. Fast charging, you're basically charging because you need to get somewhere, you need charging fast. So it actually overlaps almost exactly with the solar demand curve. That on the right is the charge sessions per hour by hour for the day. So that's really good because people have been looking for certain demand elements that match that. Because right now, the fact is it's been really hard to handle that. At least that's what we're hearing from our partners. So this is good. And also the way these stations work, sometimes having a larger connection is more economically efficient than having multiple small connections to the grid. So that we're finding that there are financial benefits also to going fast charge, as long as somebody is close and planning to be near the medium voltage grid. So there's high voltage, medium voltage, and low voltage grid. So how can today's chargers handle fast charge? Well, it just depends on the car, right? So for example, as I mentioned earlier, if you have a 350 to 400 kilowatt charger, you can handle 35 to 40 kilowatt packs in 5 minutes, right? You can still charge anything with a larger pack up to 15 minutes or so. So today's chargers can already handle that. And if you really want to emphasize that and market a car that can charge really fast in the same time as you can refuel a vehicle, but want to do that without changing all the infrastructure, you want to create cars with smaller packs. So there's already a huge movement on that. I took some photos of the various companies out there doing that. I love some of the designs, but it seems very polarizing. So the designs I like, some people really hate. But in any case, that's why it's wonderful to have so many different vehicles out there. But likely, we're going to see this evolutionary approach. We're going to see using existing infrastructure, using cars, and then building on top of that rather than something coming up and changing everything. But it is through collaborations with all sorts of companies, from technology developers like us or academia, research labs, to industry heavyweights, including energy companies, auto companies, aerospace companies, infrastructure and regulatory bodies. And we're having conversations with all of that. I think in some ways we're having more conversations with companies that are further away from us than local. So that's one of the reasons I'm here. Hopefully we can actually engage more of that, because I think a lot of our customers are based in Europe and Asia, and they've made a lot of the introductions. So I'm very excited to be part of this community and very happy that you spent some of your time to be here. Any questions?
Thank you. Microphone. This question, right? Quick question. Are you planning to stick with the
They need to record you.
Yes.
Thank you. Are you planning to stick with EVs, or are there plans in the future to move towards residential storage similar to Tesla?
We have wild goals, but I think we tend to look at the crawl, walk, run approach. So today we're working on electric vehicles and other smaller markets, such as power tools, two-wheelers, four-wheel vehicles. So those are mainly our approach today. But we have been approached by utility, home backup power, as well as grid and eVTOL applications. So that's kind of what we're looking at, but we're more focused on the electric vehicle today. But after that, we definitely would, we definitely think our technology would be applicable to all of these other markets.
Thank you. Very good presentation. Thank you very much. Looks very exciting. If we use your battery as it has been developed for slow charging, regular charging, would the quality of the battery or the charge discharge and hysteresis be the same as what it is in current batteries? Because you're focusing on this fast charging. So trickle charge, would it have the same quality of the equipment?
Yes, for our technology, if you charge it slower, it doesn't hurt the battery. So, it's capable just of faster charging. Hysteresis is a very interesting thing that you mentioned. Silicon-based technologies, including ours, does have more hysteresis than a typical graphite cell. So that does make it a challenge somehow on the pack side. But that's where I think our machine learning efforts are really, really gaining a lot of steam. We have found we can solve that by utilizing signals already within the battery that are outside of just the voltage.
Okay, since I have it, I'll ask another question too. I mean, very exciting to see how you can support the grid, okay? So you can do fast charge, and you can also do fast discharge back to the grid, right? And if you can do a fast discharge, I guess the question is, is that, once again, comes back to the reliability of the equipment. How good is it for you to be able to charge fast and discharge fast to the grid?
Yeah, I think a lot of applications on the grid or even on hybrid batteries for cars require a lot of cycles of very fast charging and discharging. And our technology can do that, but I think the requirements are different. For example, for us as a company, we still need to handle, as we get our partners ramping up in volume, we need to handle applications where there's a premium for our partners because the cost of the batteries goes down with manufacturing volume. So initially, we need to handle markets that can handle the premium first. The power grid applications are not that today. So that's why I think that's later on. Once we meet that scale, I think we will be able to handle those applications in an easier manner.
I'll ask one last question and give it. Yeah, sorry, it's already. Others may have questions. Go ahead. No, okay. And how's the market overseas, especially two-wheelers? Are there any commercial two-wheeler companies or those small auto companies that are using this, especially in Asia? Are they currently using these batteries?
So our batteries are not yet available on the market yet, but it will be within a year. So we're already working with them. We've already demonstrated it in vehicles already, but it's not available for sale yet. But that will be coming up in a few months.
Last questions?
Hi. I saw one of your slides. Are you saying you can charge your batteries at a 10C rate?
Yes.
So for an EV, you're essentially talking about 1 megawatt charging, right? So you can capable of doing that?
Well, that's why I focused on the size. Like for example, most of our customers are focused between 4C and 10C, although they have fancy algorithms which I can't talk about today. But it depends on the size, right? So for example, for a lot of the cars that people are targeting for the mass market that have smaller packs, yes, we can absolutely handle that today. But if you're talking about like 100 watt-hour pack, and then you want to charge that at 10C, that's going to be more difficult, right? So I don't think it overlaps as much. I think people with a larger pack will have more range and will probably be charging more at home, while other customers may need a fast charge where they're charging at drive-through charging stations. So it really depends on the design, and that's what's exciting about this space. It's not like, oh, we're just going to retrofit existing solutions. I think solutions are being built to address exactly what you're talking about.
And is there a detrimental effect of charging at 10C in terms of charging cycles? Like, what are your batteries like 500 cycles, couple thousand cycles?
We have many different battery designs. It's actually different for each customer. But overall, for cycle life, it's about the same as that of a conventional battery. We're not, we didn't design the batteries to be more than that. We're meeting spec on cycle life. The advantages are in the energy density and fast charge and so on and so forth. Okay.
So also, do you just use, not the regular, but the standard cathode materials, like, you're using the nickel, manganese, cobalt, or iron
we
phosphate?
have various designs that include NCM 622, NCM 811, NCMA, NCA. We have, as I mentioned, each customer has a favorite material. You kind of have to work with that. But yes, we're building cells with all of the popular cathodes out there.
Okay, great, thank you.
LFP.
How does the volatility of the batteries come into play? Are they safer? Are they like how safe are they? Because I know batteries can easily catch fire. Or, how do they compare to batteries that are on the market nowadays?
They are safer, but I always hesitate when we're talking about safety because a real story, true story. I talked to somebody and say, our batteries are safer. And like, can I staple it right now in the room? Like, no, you can't, right? So safety is very relative. Why are we safer? We don't have lithium plating on the anode side. So usually with most batteries, if you apply a high current to it on charging, you get plating on the anode side, and that can cause issues with safety. We don't have that because of our design. Two, I don't know how familiar you are, but I'll go a little bit technical here. But for thermal runaway, basically what happens is as you increase the temperature, first thing that starts degrading is the SEI layer on the anode. And that SEI layer degrades in an exothermic reaction. So once you get a temperature at a certain point, the temperature rises, right? And then what happens then is you get to the temperature where the cathode gives off oxygen, and then at that point, basically the cell will go into thermal runaway. We address that first trigger point. So our anode is different. So that SEI layer is not as exothermic, or we have difficulty detecting the exotherm there. So that's been a huge difference in terms of propagation tests. So we're safer there, but since we're using the conventional cathode and still using a liquid electrolyte, ultimately, still, you can get to the point where the cathode gives off oxygen.
Let's thank Benjamin again.
Thank you very much.
The next speaker.
Hi, everyone. Thank you for being here today. My name is Amy Lebar, and as GP mentioned, I'm a research engineer at NREL in Colorado. And after listening to Doug's introduction, I'd like to point out that NREL has just recently reached its 45th anniversary, which I believe means we've met the electronics. So we're clear to talk about electronics today. So the previous presentation on residential appliances is a really nice segue, because I do a lot of research on commercial building plug and process loads. So I want to present to you today how plug load management can enable commercial building resiliency. So quickly, just an overview of what I'm going to talk about. I'll focus first on where the commercial building industry is today, talk about the current and emerging plug load management strategies that we're seeing in buildings, how plug load management can contribute to resiliency, introduce a system called Atlas, and then touch briefly on where PPLs are headed next. So like we've heard from several other speakers, there's a big push for decarbonization across the country in many different sectors, and it's the same for commercial buildings. So we've seen that the US has greenhouse gas emission goals, and various states have carbon emission goals as well. There's been a lot of support and activity amongst organizations and building owners already to try to meet these goals. So part of the Better Climate Challenge, which is a DOE sponsored challenge, we've seen 90 companies and organizations commit to lowering their carbon emissions related to their buildings and factories. So it's been great to see that commitment already to try to meet these carbon emission goals. When we're talking about decarbonization for commercial buildings, we're primarily interested in improvements in efficiency, electrification, and then control of the building loads. So I do research on plug and process loads in a commercial building. So they are all plug-in and hardwired electrical loads within the building that are not associated with another major end use. And as Kim mentioned, they account for 47% of commercial building energy consumption today. And that's expected to increase as other building end uses continue to become more efficient, and as more electronic devices enter commercial buildings. So there's huge potential for energy efficiency or energy savings, and also carbon savings by targeting these plug and process load devices. There's a couple ways that they can contribute to low carbon strategy. The first of which is just efficiency. If we look at the decarbonization priority waterfall over here, energy efficiency is the first area that building owners should target before they consider doing on-site or off-site renewables or looking into carbon offsets. Just getting that base load as low as possible is hugely important. This can be done through consolidating devices within the building, installing Energy Star certified equipment, or installing control technologies, some of which I'll talk about a little bit later. Another way that plug and process loads can contribute to low carbon strategy is just electrification. In this realm, commercial plug and process loads were primarily focused on kitchen and laundry equipment. An important thing to note here is, these buildings that are partially gas-powered and electric-powered likely don't have the electrical system to support these high power electric devices. So these updates will need to be made to these buildings. And then finally, integrating plug and process load controls with the building automation system. This is something that is in emerging technology. It's definitely newer when we talk about plug and process loads, but really having the building being able to understand and manipulate all of the loads within the building, not just lighting and HVAC, allows them to respond to grid signals. And this will become increasingly important as more renewables come online. So I wanted to talk about some of the technologies and strategies that we're seeing in current commercial buildings to give you an idea of where we're at. So behavior is incredibly important when we're looking at plug and process loads, both in residential and arguably even more so in commercial buildings. In residential buildings, the people that own the appliances are the ones that are interacting with it. And if they install a control strategy, they understand it, they feel motivated to make the control strategy work. Whereas if you are looking at a commercial building, you have hundreds, if not thousands, of occupants that could be interacting with these devices. So really getting everyone on board is hugely important for when we're talking about commercial building plug load management. So Cornell has done, their main focus has been on behavioral efforts. So they've done a lot of community-based social marketing and campaigns to promote sustainable behaviors amongst their students and faculty. And this has been fairly successful, just powering down their plug-in devices when they're not in use. Seems very simple, but is quite effective. Procuring Energy Star certified devices, and then in some cases using plug load controls like advanced power strips and smart outlets. Sleep settings are another strategy that we're still seeing being implemented in commercial buildings. The Community College of Allegheny County saved 74% on their computer energy consumption just by implementing sleep settings. So a fairly simple strategy, but can be hugely effective. And again, wanted to note that they really engaged their occupants and communicated what strategy they were using so that the engineering control would be successful. We also see whole building approaches to plug load management. This is the research support facility at NREL. It was constructed about 10 to 12 years ago. And so the engineers during the design and commissioning process looked at the whole building's plug loads to figure out strategies for reducing the energy consumption, such as consolidating devices, procuring Energy Star certified equipment, installing advanced power strips, which are little controlled power strips to reduce the unoccupied load, and then also just making sure they turned on timers and auto off on devices like coffee makers. We also see more large-scale control systems being installed in buildings. This is the Houston Advanced Research Center, and they installed a smart outlet system. For those that aren't familiar, a smart outlet is a little device that sits between the wall receptacle and your plug load device, and it controls whether electricity flows to it. They're usually wirelessly connected to a central system so that controls can be applied. And they also have energy metering capability, so that is gathered. So what HARC was really interested in primarily was the metering functionality of this at first, understanding what devices in their building consume the most energy, opportunities for savings, but then the control benefits of a system like this also reduced their overnight load, which they found hugely beneficial. Something that's been coming on, we've seen more in pilot projects, is integration. So this can be with in this instance, integrating your plug load control system with the lighting control system. So the Minnesota Department of Transportation had this pilot project that they did over the last couple of years, and they tied their automatic receptacle controls here with the occupancy sensors that were also used by the lighting system. So when a zone became unoccupied, both the lighting and the controlled receptacles would turn off. They also had really great communication with their occupants to enable the success of this. And then finally, taking the integration a step further and integrating plug load controls with the building automation system. This is hugely important when we start to think about responding to grid signals, grid interactive efficient buildings. What they're primarily interested in this project is sharing the data between the building automation system and the plug load controllers to enhance the performance of both systems. So using some of the sensor inputs as part of the larger building automation system to inform the plug load operation and then vice versa. So this is a cool project that has been going on for about a year so far, and I think they have a couple more years left. And then briefly wanted to mention a couple features of plug load management systems that are emerging on the market, one of which is automatic and dynamic load detection. So this allows your plug load management system, whether it's automatic receptacle controls or smart outlets, to detect what device is plugged in based on the electric consumption profile. So that will definitely make the systems more plug and play. And then learning behavior algorithms, like the name suggests, they learn the occupant behavior and will create optimized schedules to really maximize the energy savings of your plug load management system. All right, so all of the technologies and strategies I just mentioned are really focused on energy savings and carbon emission reductions, which are definitely very important areas of research and work. But as we experience more climate change related events and power outages, a huge area of work in commercial buildings moving forward is going to be resiliency. The Merriam-Webster definition of resiliency is an ability to recover from or adjust easily to adversity or change. And if we take a definition more related to commercial buildings, it's the ability to protect, maintain, or restore the functionality of, value of, and income generated by a building after a damaging event or circumstance within a prescribed time frame. So based on that definition, commercial buildings that are resilient should be able to respond to grid signals and operate in grid-independent mode. By grid-independent mode, I mean rely on either on-site renewables or on-site storage or both to maintain the function of the building if there is a grid outage. So again, let's look at how PPLs can enable resilient buildings. The categories I have listed probably look similar to the decarbonization, but when we're thinking about resiliency, we're thinking about these categories in a different way. So for example, for efficiency, rather than just saving energy and carbon emissions, we're thinking about the building being less of a burden on the grid and having lower energy requirements to be powered by on-site renewables. Integration, we have the different systems across the building speaking to one another and sharing information about which functionalities of the building, which systems need energy at different times. And the big piece here for the grid interactive capability is knowing when, but mostly knowing how to curtail a building's loads. And that's been a huge challenge for plug load management systems in the past, is just knowing what's plugged in, what characteristics each of these devices have. Like for instance, if a device has a built-in battery, what charge is that battery at, and can we cut power from it for an hour, and will it still be able to function for the occupant? So that's kind of the frame of reference that we're looking at these categories in. So the energy efficiency piece we have handled fairly well with the current technologies and strategies that are out there today. But the integration and grid interactive capability, we're missing some capabilities of current systems. This is largely due to the fact that the current plug load management technologies are not automated and do not have centralized control of all PPLs in the building. When we look to the residential sector, we see an uptake in smart home management systems like Amazon Alexa or Apple Home that take advantage of Internet of Things connected devices to control the devices in the home and get a sense, it can schedule, maybe run your dishwasher at 2 p.m. when there's a lot of solar generation. But we have not seen this for commercial buildings. So our team at NREL noticed this and realized that there's an opportunity to take advantage of these connected devices and move them into a commercial plug load management system. So that brings us to Atlas. Atlas is the automatic type and location identification system. It's a plug load management system framework that Kim and I developed along with a couple of our colleagues at NREL. And it takes advantage of Internet of Things connected devices to automatically identify the location, energy use, and operating state of every plug-in device in a commercial building. So I'll talk briefly here about how Atlas would function. Every connected device would have an RFID reader on its plug, and every outlet within the building would have an RFID tag that corresponds to its location. So when the device is plugged in, it reads the tag, then knows, okay, I'm in conference room A, and it'll communicate this information wirelessly through a central control hub to a system dashboard for the building operator to access. The devices are also able to self-meter, and this metering information would also be sent wirelessly to the dashboard. Controls go the opposite way, and one of the distinguishing capabilities of Atlas is that the device implements the control itself. So rather than just cutting the power to the device in the form of a smart outlet or automatic receptacle, the device would receive a control instruction to power down, and it would do so following the manufacturer prescribed protocols. So this becomes important when we're considering devices that are typically excluded from plug load management systems like projectors. If you cut the power to a projector, it could potentially damage it because it doesn't follow the proper procedure to shut off. So this would allow the plug load management system to be more inclusive. And then over here in the corner, you see we have a database which will just store all the historical data and also provide an inventory of devices within the building. So the three technologies that I mentioned earlier in the presentation are great at reducing energy consumption, but for that integration and grid interactive piece that we need for resilient buildings, there are some capabilities that are missing. So smart outlets are the most advanced of these technologies. You're able to shut off power based on a schedule. They'll meter energy. Some of them have load identification where they infer the device type based on the electric consumption, which makes them somewhat plug and play. This is an implicit identification method. With Atlas, this would be Atlas has an explicit identification method, meaning when a device is plugged in, it knows what it is with certainty, and it can communicate that information to the central system. Atlas also has location identification, which is a new capability that has not been seen in plug load management technologies to date. And that's important for just knowing where devices are being used within the building for both energy and non-energy benefits. So briefly wanted to talk about some of Atlas's applications, the first of which is virtual emergency circuits. In typical commercial buildings, they will have a hardwired emergency circuit that will allow certain critical devices to remain on during a blackout. This is especially useful in hospitals, so that the generator can power the limited number of devices. These are great, except when space needs to be reconfigured for any reason. These can be really expensive because you have to rip out the wiring from the walls, and it's also really time consuming. So with a system like Atlas, we could have virtual emergency circuits in which certain devices are permitted to be on no matter where they are in the building during brownout or blackout, and all other devices are instructed to be off. Grid interactive buildings, efficient buildings, we've talked a bit about, but really knowing what is in the building and what properties each of the devices or characteristics each of the devices has within the building is hugely important for curtailing energy use. Automated energy audits, typically the PPL portion of an energy audit is very time consuming and tedious, but all of this data would be stored in an Atlas system and could just be transferred over to the auditor. And then finally, asset management. This is both the equipment within your building, understanding when it's close to end of life and may need to be replaced, but also the building space itself. So knowing where devices are being used, maybe there's one of the kitchen areas in your office, you notice like none of those devices are being used. It could indicate that maybe you don't need that kitchen space and it could be repurposed, or your office could downsize if you need to. So Atlas we imagine it being used in all commercial building types. These four are likely early adopters. K through 12 schools have been early adopters of plug load management technologies previously, so we think it would be the same for Atlas. And the healthcare industry, I think, could really benefit from the virtual emergency circuit capabilities of Atlas. All right, so just wanted to wrap it up with where we think plug and process loads are headed within the next couple years. We expect to see more work with codes and standards. Our team has been working on automatic receptacle control, standardization of labeling. We also expect there to be more pilots and integration projects with plug and process loads and other building systems. And then also we expect to see a lot more validation of these emerging PPL technologies, both lab scale and within buildings. So thank you all very much for your time, and I'm happy to take any questions.
Thank you. It's open for questions.
Thank you. Question of quantification of savings potential. NREL analyze that.
For Atlas or other?
I guess specifically Atlas.
Yeah, so no, we have not gotten to that part of the research development of the system. Atlas at this point is a framework that could be implemented in other plug load management systems. However, we have seen that there is about 30% energy savings with other plug load management technologies. So I would imagine around 30%, if not a little bit more.
Can you, hi. Me question. Notice the at tag was on the plug and the reader was on your power cord. What is the rationale for doing it that way for the other?
Yeah, just go back to that. Right, so the idea behind that is that the outlet will be passive, so it will just have the tag on it, whereas the reader will be connected to the Internet of Things device that has that communication capability to communicate that information to the central system. Does that answer your question?
One second. We'd like to record your questions.
Oh, thank you. So what would the implications be if you swap those two things? In other words, I guess I'm assuming that the reader would actually be a costlier item than the tag. And so why not embed tags in all the devices and then through ID or databasing be able to get all the profiles and the characteristics of the device?
Yeah.
Anyway, I was just kind of curious. Thanks.
Yeah, so I believe if we had the RFID reader on the outlet, we would have need to somehow communicate what the reader is reading to the system. So if we put it on the outlet, just on the faceplate, we would then need to make the faceplate connected somehow, either wirelessly or through a wired connection, which would make installation a bit more time consuming for this type of system. Yeah, good question.
I actually had the exact same question, but I think in both cases, right, you've got to communicate whatever is coming in the tag or the reader, either back to the device or to the wired infrastructure to some system, so that's a challenge. So given that challenge, even if it's on the plug part, right, the wires or whatever to bring it back to where the Wi-Fi radio is or something like that, it will definitely be challenging. I'm wondering if you're also considering other means of location. I know at least Wi-Fi and Bluetooth are all working on some location things, so it may not be as precise, and it won't tell you which circuit it's on. But perhaps there can be some other things, or coordination of if the device realizes it's taking some power, you can kind of correlate that back onto which circuits it's on. But that location path will definitely be a challenge. So you might want to be open to other means of determining location. Yeah.
Yeah, those are great points. We hadn't considered the Wi-Fi piece. Some of the other options we'd considered was if power over Ethernet becomes more commonplace in buildings, using that, or potentially like USB. But yeah, the Wi-Fi piece is a good point. Thank you.
Staying with the same thing, just tell us, what I'm seeing there is like a printer, okay? I'm assuming when you say energy use, it's a real-time kilowatt hour that the printer is consuming. So how is that measured? How is that measured and relayed?
Right. So we've seen quite a bit of research on self-metering devices. A lot of that research coming out of Lawrence Berkeley Lab. So at this point, we would, many of these devices do have the capability built in for self-metering, but a lot don't at this point. So this would be working with manufacturers to get that capability installed in their devices. And then the communication pathway would just be however IoT devices typically communicate with a central system.
With the rapid growth of IoT and the chip shortage, do you see a hampering of your timeline for implementation?
Great question. So we don't have a specific timeline yet per se. We are still in the idea and piloting part of this project development. So I think that will be an issue down the line if we continue to see these shortages. But at this point, it's not an issue.
Any other questions? If not, let's thank speaker again, Amy.